In the name of Almighty God, I am Mahsa Sankoshi, and today I want to talk about submarine high frequency asymptotic scattering. The primary defense of a submarine lies in its capacity to remain hidden during operation. As radio waves are strongly absorbed by seawater, sound navigation ranging or sonar is one of the main methods used for the detection of submarines. Sonar systems are also used for underwater exploration as well as in the fishing industry. Designers analyze the way acoustics waves are reflected in order to minimize the equivalent reflecting area of the submarines. This simulation studies the scattering of the BeTTSi benchmark submarine benchmark target echo strange simulation. This model uses the high-frequency approximation of the pressure acoustics asymptotic scattering interface. The analysis is fast and a good approximation at high frequencies when the wavelength is much smaller than the scattering object. High-frequency asymptotic methods for analyzing the EM scattering by open-ended waveguide cavities for high-frequency methods are described for analyzing the electromagnetic EM scattering by electrically large open-ended cavities. They are the first one a hybrid combination of waveguide model analysis and high-frequency asymptotics. The next one and the second one is geometrical optics or GORA shooting. And the third one is the Gaussian beams or GB shooting. And fourth one is the generalized ray expansion or GRE method. The hybrid model method gives a very accurate results but is limited to cavities which are made up of sections of uniform waveguides for which the model fields are known. The GeoRay shooting method can be applied to much more arbitrary cavity geometries and can handle absorber-treated interior walls, but it generally only predicts the major trends of the RCS pattern and not the details. Also, a very large number of rays need to be tracked for each new incidence angle, like the GeoRay shooting method. The GB shooting method can handle more arbitrary cavities, but it is much more efficient and generally more accurate than the GEO method because it includes the fields diffracted by the rim at the open and which enter the cavity. However, due to beam divergence effect, the GB method is limited to cavities which are not very long compared to their width. The GRE method overcomes the length to width limitation of the GB method by replacing the GBs with GORA tubes which are launched in the same manner as the GBs to include the interior rim diffracted field. This method gives a good accuracy and is generally more efficient than the GEO method, but a large number of ray tubes needs to be tracked. And the next chapter is asymptotic expansions of high frequency multiple scattering iterations for sound hard scattering problems. We consider the two-dimensional high-frequency plane wave scattering problem in the exterior of a finite collection of disjoint, compact, smooth, strictly convex obstacles with Newman boundary conditions. Using integral equation formulations, we determine the Hormander classes and derive high-frequency asymptotic expansions of the total fields corresponding to multiple scattering iterations on the boundaries of the scattering obstacles. These asymptotic expansions are used to obtain sharp wave number dependent estimates on the derivatives of multiple scattering total fields, which in turn allow for the optimal design and numerical analysis of Galerkin boundary element method for the efficient and frequency-independent approximation of sound-hard multiple scattering routines. Numerical experiments supporting the validity of these expansions are presented. High-frequency scattering problems considered in this manuscript have been effectively tackled using asymptotic approaches such as the Ray method or RM and geometrical optics or GEO. These methods are based on Ray in the short wavelength limit, which take the form of asymptotic series of amplitudes in inverse powers of the wave number co-modulated by the oscillations in the incident field of radiation. The resulting Iconal equation for the phase and the recursive system of transport equations for the amplitudes are independent of frequency. The diffraction effects ignored in RM and GO are taken into account in refined approaches such as the uniform theory of diffraction and geometrical theory of diffraction. While implementations based upon asymptotic methods are frequently independent and the accuracy increases with increasing frequency, they are not designed to converge for fixed frequencies. On the other hand, in the case of low to moderate frequencies, classical schemes based on direct discretizations of differential equations such as the finite different time domain method, variational formulations including the method of moments, the finite element method, the finite volume method, and integral equation formulations including the accelerated ones using hierarchical metrics and fast multiple method have been successfully used in the design of numerical algorithms for wave propagation problems. Methods that combine the advantages of classical schemes, for example, error control, controllability, and asymptotic methods, for example, frequency independent degrees of freedom, and that thereby provide simulation strategies applicable over the entire frequency spectrum have been the context of increasingly active research in the last decades, and their references therein. In this context, approaches that combine asymptotic expansions and integral equation formulations have displayed the capability of delivering frequency-independent accuracies with the utilization of number of degrees of freedom that needs to increase only mildly with increasing frequency. Moreover, some of them are frequency independent. These methods can be classified as corresponding to single or multiple scattering problems. For the case of single scattering, the problems considered correspond to smooth strictly convex obstacles, convex polygons, and screen and apertures, and half-plane for general review and for high-frequency properties of integral operators. On the other hand, algorithms relating to multiple scattering configurations are significantly more demanding due to the nature of problem. In this connection, the boundary element methods proposed for a convex polygon in addition to several small obstacles and a non-convex polygon both demand on O logarithmic k increase in the number of the degree of freedom to maintain accuracy with increasing frequency. While on the other hand, while on the one hand, the method doesn't require iteration, for example, through a utilization of Newman series and thus ray tracing, it is not applicable over the entire frequency spectrum since small obstacles are required to have sizes on the order of the wavelength to preserve the O logarithmic k efficiency. The case of a non-convex polygon considered in allows for only finitely many reflections and thus a finite ray tracing procedure. The case of several smooth compact strictly convex scatters with no restrictions on their size with respect to the wavelength treated in this simulation is a multiple scattering problem resulting in infinitely many reflections and trapping relations. The related scattering problem was initially studied in the context of the Dirichlet boundary condition. In this simulation, the multiple scattering formulation is based on a Newman series decomposition applied to integral equation formulations and three dimensions. Here in the case, the Newman Sound-Hard boundary condition, we reduce the multiple scattering problem to a collection of single scattering partial differential equations. Our main contributions are the derivation of the asymptotic expansions of the total fields associated with multiple scattering iterations on the boundaries of scattering obstacles, and of sharp wave number dependent estimates on the derivatives of these densities. As we shall explain, these estimates are fundamental in the design and numerical analysis of efficient frequency-independent boundary element methods for the iterated solutions of multiple scattering problems. In addition, we present numerical tests validating the asymptotic expansions derived. As we mentioned, the two-dimensional multiple scattering problem we consider here was studied here for directional boundary condition. The asymptotic expansion derived therein regarding the normal derivative of the multiple scattering total fields were used to design efficient frequency-independent Galerkin boundary element methods for Dirichlet multiple scattering problem. Generally speaking, the approach was an extension of the single scattering algorithms to multiple scattering problems. For a plane wave, incidence U in x and k is equal to E with the direction of alpha impinging of a single on a single smooth convex obstacle subject to the Dirichlet boundary condition. The key element in the design of Galerkin approximation spaces here were phase extraction and the asymptotic expansion where we develop here in this simulation from the main element in the extension of the Galerkin boundary element methods proposed for the Newman boundary condition for to the case of several smooth convex obstacles for the efficient or frequency dependent approximation of multiple scattering iterations. Another application of these expansions is the possibility of studying of the rate of convergence of multiple scattering iterations as down here for the Dirichlet case. The simulation is organized as follows. In the next part, we introduce the sound-hard scattering problem, discuss the single scattering Melrose-Taylor asymptotic expansion of the total field and present multiple scattering formulation. In the next one and next section, we set technical assumptions and summarize the geometry of multiple scattering rays. In the same section, we present two of the main results of the simulation. They concern the asymptotic expansions of the multiple scattering total fields on the boundaries of the scattering obstacles and sharp wave number dependent estimates on their derivatives. And the next section is reserved for the statement and proof of the third main result relating to the asymptotic expansions of the iterated scatter fields. And finally, numerical results validating the asymptotic expansions derived in the theorem are presented in the last section. In this simulation, we derived the asymptotic expansions of the solution of multiple scattering problem with a Newman boundary condition. These expansions allowed for the driven derivation of sharp wave number dependent estimates related to their derivatives, or more generally on the derivatives of envelopes obtained by subtracting finitely many terms in their asymptotic expansions as presented in the theory. These estimates in, in turn can be used to extend the Galerkin boundary element methods for sound hard single scattering problem to multiple scattering scenarios for frequency independent implementations. The next chapter is numerical asymptotic boundary integral methods in high frequency acoustic scattering. In this simulation, we describe recent progress on the design, analysis, and implementation of hybrid numerical asymptotic boundary integral methods for boundary value problems for the Helmholtz equation that model time harmonic acoustic wave scattering in domains exterior to impenetrable obstacles. These hybrid methods combine conventional piecewise polynomial approximations with high-frequency asymptotic to build the basis functions suitable for representing the oscillatory solutions. They have the potential to solve scattering problems accurately in computation time that is almost independent of frequency, and this has been realized for many model problems. The design and analysis of this class of methods requires new results on the analysis and numerical analysis of highly oscillatory boundary integral operators and on the high-frequency asymptotic of scattering problems. The implementation requires the development of appropriate quadrature rules for highly oscillatory integrals. This simulation contains a historical account of the development of this currently very active field, a detailed account of recent progress, and in addition a number of original research results on the design and analysis and implementation of these methods. Acoustics, elastic, and electromagnetic wave scattering problems arise in many applications of mathematical, physical, and engineering interest, including the modeling of radar, sonar, noise barrier design, and atmospheric particle scattering. Often the scattering problem comprises the forward map in the formulation of an inverse problem, for example in non-destructive testing or in methods for detecting hydrocarbon-bearing deposit under the seabed. While in general the scattered wave has to be found in an inhomogeneous medium, there are substantial number of applications in which the material is either homogeneous or piecewise homogeneous, at least sufficiently far away from the scatter. In these cases, the boundary integral equation or BIE methods are of considerable interest and form the basis for several commercial scattering codes uh, in this section. Submarine acoustic target strange modeling at high frequency asymptotic scattering uh, will be our next chapter. The ability to identify asymptotic scattering is critical for the continuous operation of modern combat systems. In the active sonar equation, acoustic target strange is crucial. The plane wave propagation target strange equation predicts far-field radiated intensity. Submarines defend themselves by being invisible. Sonar can be used to detect submarines. Saltwater readily absorbs radio waves. Commercially, fishing and scientific ocean exploration both make use of sonar technology. Acoustic wave reflection reduces the area requirements of ocean depth sections. Therefore, submarine designers take this into consideration. The target range or TS of a sonar target is used to assess its size. The pressure acoustic boundary element model or PRBEM of the high frequency boundary model or HFB illuminates and simplifies the TS analysis of the benchmark target echo strange simulation. Benchmark submarine. We explore how subsea shape, material qualities, and operation frequency affect acoustic target strange using comprehensive models. The findings underline the need of correctly characterizing the structural sections of the submarine and their impact on the dispersion. They also help with research into the submarine acoustic signature, detectability, and potential detection mitigation measures. Index terms target strange pressure acoustic sonar boundary element model asymptotic can be the next one. One of the primary advantages of using a submarine for military purpose is the fact that its operator may stay out of sight. The primary motive behind the development of the submarine was the significant reduction in the optical footprints that can be detected. But not long after that, it was discovered that there were other indicators that could be used to look at submarines. Due to the ease with which sound travels through water, it is possible to identify the presence of submarines under normal diving conditions using simple sound. In the detection industry throughout the course of previous few decades, passive sonars have been nearly unrivaled in their prevalence. They were successful in determining the source of the submarine's acoustic noise and locating it. As a direct consequence of this, the acoustic noise that the submarines were producing was carefully mitigated. Active detection sonars are utilized by a number of native names since passive sonars have difficulty detecting most of modern submarines. In the active sonar detecting sector, it is the utmost importance to reduce as much as possible the tendency of the submarine to reflect the incoming acoustic energy as target echo strange or TES. Sonar was an essential component in the development of new submarine technology, which was in a state of perpetual flux. The procedures on their own were improved upon. The ever increasing computer calculating ability has been of great assistance to sonar technology, which has led to beams that are geometrically more precise and data processing methods that are more intricate. The processing of signals that has a great deal of potential is made even more appealing by the data synthesis capabilities of networks that can be either bi or metastatic. It has been proved that using this strategy can greatly extend the detecting range of contemporary submarines, which will experience a rise that is orders of magnitude greater in the years to come. In order to submarines to keep their existing tactical edge in the future, they will need to have access to TES reduction technology, refraction, which is induced by the variation in the speed of sound, which depth allows sound to travel through water at long distances, such as those that encounter in underwater sonar applications caused by changes in temperature, density, and salinity. As a consequence of this, the sound waves that a submarine hears could not be exactly parallel to the horizontal plane. It is possible that reducing the TES in a submarine will need to only horizontal TES reduction but also vertical TES reduction across a number of different heights. This angular range, sometimes referred to as the danger zone, is estimated for the purpose of conducting research on the dissemination of sounds over the oceans of the world. After then, the shape of a traditional submarines is compared to the TES optimized shape of submarines, which is derived from the latter. The capacity of submarine to operate without being detected is its primarily defense. Sonar or sound navigation and ranging is a common method for locating hidden submarines. This is due to the fact that water at sea level absorbs radio waves quite well. Sonar systems are employed not just in the fishing sector but also in underwater research. The submarines designers consider the reflection of acoustic waves in order to minimize the amount of space required for such reflections. This development delves deeply into scattering near the BeTTSi benchmark submarine at high frequencies. The border between pressure acoustics and asymptotic scattering is approximated in this model. When the frequency is high enough, the wavelength is significantly less than the scattering item, hence the analysis is quick and accurate. Target strength is a metric that can be used to calculate the size of a sonar target. The majority of submarines have absorptive materials applied to the exteriors of their bodies to reduce the strength of the backscatter signal. When only one angle of incidence and frequency are considered, the model computes the force imparted to the target. Because of the model's versatility, the model's scope can be easily expanded to include a variety of frequencies and geographical origin. Submarine technology, including sonar systems as well as the processes involved in their operation, have been regularly enhanced and improved. Sonar technology has profited considerably from the improved computing power, resulting in more precise beams and more complicated data processing procedures. Utilizing the data synthesis capabilities of a bi or multi static network can improve perspective signal processing technology. Because this approach has been demonstrated to be effective, it is fair to expect that the that detection range for modern submarines will dramatically extend in the near future. Submarines will need to use TES reduction technology in the future to maintain their tactical edge. Underwater applications of sonar demonstrate how sound can travel enormous distance through water, with the speed of the sound varying with the depth due to variations in temperature, density, and salt, and being reflected at the water surface. Due to the fact that submarines don't travel at the same depth as the surrounding water, the sound waves that strike them cannot originate from a precisely horizontal place. It will not be sufficient for submarines to just have their TES decrease. Rather, the TES will need to be modified downward at many heights. This angular range, also known as the hazard sector, is utilized for the planning of sound propagation research. This research was undertaken in various oceanic regions across the globe. Then we contrast a conventional submarine design with one that was modified and optimized for TES. Submarine utilize a well-kept cover tail to describe their primary form of defense while in operation. Due to the numerous attenuation of radio frequencies in water, sonar is the most used method for locating submarines. When designing submarines, engineers take into account the reflection of acoustic waves in order to determine how to limit the subsurface area that is responsible for reflecting sound. A sonar system's target strange metric can be used to estimate the size of sonar target. Submarine exteriors are frequently coated with substances that absorb signals that have been backscattered from them. The use of synthetic aperture sonar (SOS), as demonstrated by references which I will describe here, represents an intriguing possibility to greatly improve the accuracy and detail of target strange modeling. Synthetic aperture sonar systems have proven to be capable of producing high-resolution photographs of underwater targets, capturing detailed features with unparalleled clarity. To improve the scientific discourse, the authors must go into the intricacies of adding source data into target strange modeling. A description of the approach used to extract useful acoustic information from source majoring the advantage of high resolution in characterizing target characteristics and the consequences for refining and optimizing target strange models might be included. Furthermore, the authors could investigate any special obstacles or considerations associated with incorporating such data into the modeling processes. By addressing these issues, the work has the potential to be a helpful resource for researchers and practitioners interested in using the enhanced capabilities of synthetic aperture sonar in the context of underwater acoustics and target strange modeling. A problem statement: the major goal of this research is to create a model for submarine vehicles acoustic target strange in an underwater environment with a focus on high-frequency asymptotic scattering. The term acoustic target range refers to the effectiveness with which an object scatters or reflects sound waves back to a sonar system. The detectability and identification of underwater targets, particularly in the context of submarine vehicles, are critical in both the Navy and scientific sectors. The primary focus of this research is on the phenomena of high-frequency acoustic scattering, which is frequency observed in the ultrasonic or high-frequency spectrum, typically surpassing a few kilohertz. The use of high-frequency scattering is critical for precise target recognition and classification, especially complex underwater environments. The goal is to develop a mathematical and numerical model that accurately depict the phenomena of acoustic scattering induced by high-frequency underwater submarine vehicles. The proposed model should be built by including the fundamental concepts of high-frequency asymptotic scattering theory while taking into account the vehicle's intricate characteristics such as its complicated shape, size, and material properties, and also to investigate the effect of various parameters on the acoustic target strength. The angle at which the incident sound wave impacts the target, the frequency at which the sonar system operates, and the vehicle's material property are among these elements. And the next chapter is motivation. There is reasoning for predicting acoustic target strength for high-frequency asymptotic scattering in underwater submarine vehicles arises from its importance in a variety of aspects, enhancing submarine stealth and concealment, improving anti-submarine warfare capabilities, assessing the environmental consequences of underwater operations, developing effective defensive strategies, advancing scientific exploration in underwater acoustics and oceanography, optimizing sonar systems design, and serving military and national security objectives are among these. By precisely predicting uh, the acoustic target intensity at high frequencies, this simulation aims to provide useful insights into the construction of quieter and less detectable submarines. This discovery has a major ramification since it can improve naval forces' ability to detect and track possible threats, safeguard marine ecosystems, develop countermeasures against hostile sonar systems, and progress undersea technologies. Finally, these developments will help to make undersea operations more effective and secure in a variety of fields. Several key limitations and deficiencies have been observed in analyzing relevant publications addressing the modeling of an undersea submarine vehicle's acoustic target range for high-frequency asymptotic scattering. For starters, one common disadvantage is the dependence on simplistic theoretical models that fail to fully describe the intricate interactions between the submarine's geometry, materials qualities, and the surrounding medium. These simplified models frequently fail to account for the subtle nuances of dispersion, resulting in mistakes and limited applicability in real-world circumstances. Second, most existing studies tend to focus on specific geometric configurations or materials, ignoring the generalization of target strength prediction across different submarine designs and materials. This lack of generality impedes a more comprehensive knowledge of target strength behavior for many types of submarines. Furthermore, previous research has mostly focused on low to intermediate frequency ranges, ignoring the critical high frequency domain where the scattering effects grow more intricate and important for underwater detection systems. As a result, knowledge of high-frequency asymptotic scattering and its impact on target range is still restricted. Furthermore, the lack of experimental validations of the presented models limits confidence in their predictive accuracy, emphasizing the need for more detailed experimental studies to validate the theoretical predictions. Finally, despite their major impact on target range estimations, environmental elements such as sound speed profiles and seabed properties have been largely ignored. It is critical to address these limitations in order to improve the reliability and practicality of acoustic target range models for high-frequency asymptotic scattering in underwater submarine vehicles. And what about the research question? The first one is how can the acoustic target strength of an underwater submarine vehicle be effectively modeled using high frequency asymptotic scattering? The next question would be how can the high frequency asymptotic scattering model be applied to underwater submarine? The third question is how accurate and reliable is the high frequency asymptotic scattering model compared to other methods? The following is a summary of the manuscript's most important contributions. We deploy acoustic target strange for underwater submarine vehicles to facilitate the development of stealth technologies. This is shown to improve underwater communications, and feed target strength is evaluated using various acoustic pressure settings, which helps in understanding how a target or object interacts with sound waves and provides insights into its scattering properties. The levels of scattered acoustic sound pressure are assessed using a polar plot and a line graph. In addition, we analyze the radiation pattern, which helps in understanding the spatial distribution of sound energy radiated by a source or scattered by an object. We analyze the high-frequency asymptotic scattering of a smaller wavelength scattering object so as to obtain detailed information about its properties and behavior. Based on the desired performance metric, we recommend appropriate scatter acoustic sound pressure levels for underwater networks. The remaining part of this work is organized as follows. The theoretical notion of a model is explained in the next section, while in the third section describes both the design model and the technique. On the other hand, a comparison and discussion of the acquired data is elaborated in the fourth section. Finally, the fifth section provides the conclusion and research scope. And what about the theoretical basis of the proposed model? And we can visualize a sphere-shaped wave approaching the bow of the submarine from the distance of 1,000 meters and at an angle of phi equal to 360 degrees using the background pressure field. By the time the waves reach the submarine, they have already acquired the characteristics of plane waves in this location. When the simulation is run, the ocean attenuation material stands in for the inherent losses associated with the transmission medium. Because its parameters are obtained from a large amount of experimental data, this attenuation model can be considered semi-analytical in nature. There are other more parameters that contribute to the depth, temperature, salinity, and pH. Purpose acoustic target strange as modeled by COMSOL simulation. During the simulation, the ocean attenuation material replaces the transmission medium's intrinsic losses. Because its parameters are derived from a significant amount of experimental data, this attenuation model is semi-analytical in character. Other factors such as the viscosity of pure water, the relaxing activities of boric acid, and magnesium sulfate, to name a few, play a role in addition to depth, temperature, and salinity, and also pH. The impedance border condition is set to the absorption coefficient to represent a soft material resting on one of the hard surfaces. And you can see here in simulation illustrates the predicted amount of acoustic target strength as determined by COMSOL simulation and using the Helmholtz Kirchhoff integral and the finite element method or FEM. For the acoustic solid cupped model, the strength of the target was calculated. The Helmholtz and Kirchhoff integral is a mathematical equation that describes the wave propagation of sound or electromagnetic waves in free spaces. It combines the Helmholtz equation, which governs the behavior of waters, with the Kirchhoff integral theorem, which provides a solution for the field at a point in terms of the sources surrounding that point. The Helmholtz equation is given by delta is power by 2 phi plus k power 2 omega is equal to 0, where phi represents the wave field, k is the wave number, k is equal to 2p divided by lambda, where lambda is a wavelength, and delta 2 is the Laplace operator. The Kirchhoff integral theorem states that the phi at a point P, due to a distribution of sources in surrounding region V, can be expressed as an integral over the surfaces, enclosing the volume V. Mathematically, it is written as in the next equation: phi p is equal to uh, a quarter p and the integral of phi differentiation from volume and differentiation number minus a differentiation of omega and differentiation of v and n, where omega differentiation v represents the wave field on the surface S, and the differentiation of n is the outward normal deviation on the surface S, and ds represents the surface elements. And what about the Helmholtz equation? In mathematics, the Helmholtz equation is the eigenvalue problem for the Laplace operator. It corresponds to elliptical or partial differential equation, which is delta phi is equal to minus k to phi, where delta d is the Laplace operator and minus k2 is the eigenvalue and f is the eigenfunction. When the equation is applied to waves, k is known as the wave number, and the Helmholtz equation also a variety of applications in physics and other sciences, including the wave equation, the diffusion equation, and the Schrödinger equation for a free particle. In optics, the Helmholtz equation is a wave equation for the electric field. The equation is named after Hermann von Helmholtz, who studied in it about the year of the 1860. The Helmholtz equation often arises in the study of physical problems involving partial differential equations or PDEs in both space and time. The Helmholtz equation, which represents a time-independent form of the wave equation, results from applying the technique of separation of variables to reduce the complexity of the analysis. For example, consider the wave equation. Separation of variable begins by assuming that the wave function is in fact separable. Substituting this form into the wave equation and then simplifying, we obtain the following equation, and notice that the expression on the left side depends only on r, whereas the right expression depends only on t. As a result, this equation is valid in general case if and only if both sides of the equation are equal to the same constant value. This argument is key in the technique of solving linear partial differential equations by separation of variables. From this observation, we obtain two different equations, where we have chosen without loss of generality the expression of minus k2 for the value of the constant. It is equally valid to use any constant k as the separation constant, and k2 is chosen only for convenience in the resulting solutions. Rearranging the first equation, we obtain the homogeneous and Helmholtz equation. Likewise, after making the substitution, omega is equal to cos c, where k is the wave number and omega is the angular frequency, assuming a monochromatic field. The second equation becomes dtd, d2 dt, and omega plus omega t. We now have a Helmholtz equation for the special variable r and a second order ordinary differential equation in time. The solution in time will be linear combination of sine and cosine functions, whose exact form is determined by initial conditions, while the form of the solution in space will depend on the boundary conditions. Alternatively, integral transforms such as the Laplace or Fourier transform are often used to transform hyperbolic PDE into a form of Helmholtz equation. Because of its relationship to the wave equation, the Helmholtz equation arises in problems in such area of physics as the study of electromagnetic radiation, seismologies, and acoustic. And what about the Kirchhoff integral theorem? Kirchhoff integral theorem, sometimes referred to as the Fresnel-Kirchhoff integral theorem is a surface integral to obtain the value of the solution of the homogeneous scalar wave equation at any arbitrary point P in terms of the value of the solution and the solution's first-order derivative at all points on an arbitrary closed surface on which the integration is performed. The encloses P. It is derived by using Green's second identity and the homogeneous scalar wave equation that makes the volume integration in Green's second identity zero. Represents the submarine geometry using a mesh or CAD model. The shape and structure of the submarine are described in terms of surface coordinates and surface normals and high-frequency asymptotic scattering model. Choose the high-frequency asymptotic scattering model such as Kirchhoff approximation or physical optics pure approximation. Surface impedance model defined as surface impedance model to describe how sound waves interact with the submarine surface. The surface impedance ZS incorporates the material properties of the surface. And the fourth one is scattering equations. Scattering equations derive the scattering equations based on the chosen model. These equations describe how incident sound waves interact with the surface and generate scatter waves. For the Kirchhoff approximation, the scatter field can be expressed as follows in the next section. Which G explain Y prime Z being X Y Z is the Green's function representing the propagation of sound, which is X prime Y prime as Z prime to X Y Z. And ZS, which is impedance of X prime Y prime Z prime, is the surface impedance at the point of X prime Y prime Z prime. And peak experienced is the incident pressure at the point of the same experience as Z prime. And ds prime is the differential surface area at experience prime and Z prime. The benchmark of Submarine for this study was the benchmark target equistrange simulation. As a detailed reference of submarine target strange makes use of the geometry depicted in this simulation. This employs a pressure acoustic and asymptotic scattering physics interface to address the scattering problem. The interface assumes that the sound field in the local vicinity flat it is a high-frequency approximation. This is true if the wavelength is significantly shorter than both the critical dimensions and the surface radius. We use the Kirchhoff-Helmholtz integral to determine the radiated scatter field. Are considering surface reflection analytically. This provides us with more accurate findings. This approach is also known as high-frequency beam, abbreviated as HFM. Submarine's view of the BeTTSi and this model cannot be recognized as its dimensions are very huge in contrast to the wavelength. Under the context of the physical theory and pressure acoustics, the boundary elements are stabilized. The iterative solver will almost surely discover solutions of its if this sequence of steps is followed. If the excitation frequency approaches to 800 Hz without being stable, a substantial number of the iterations must be performed through iterative solutions. Here you can see that this is depicts the mesh view of BeTTSi. Submarines commonly apply an anechoic coating to their hulls to prevent signal dispersion. It is possible to make this absorption coefficient frequency dependent. In that case, the alpha n parameter value was used. This is only one of several possibilities. The analysis used 40 gigabytes of random access memory or RAM and took around and took around 30 minutes to execute. Due to the fact that Comsul employs virtual memory, the time required to finish the task increases if insufficient RAM is available. Target exchange or TS is critical component of underwater stealth systems. Different lines of research are carried out in order to reduce the possibility that the target would be detected. A multitude of factors can influence objective strength and including vehicle shape and construction. Sonic reflection coefficients and material used for the outer hull coating. The results of a calculation of target strength in their relation to the shape of the vehicle, the thickness of the hull, and the frequency of the acoustic wave that was hit by the vehicle are presented in this section. It was noted that a tremendous quantity of memory and speedy calculations are required to execute the procedure. This is due to the size of the vehicle and the comparatively high frequency of the incident acoustic waves. To address this issue, we create and build a scaling mechanism for the car that reduces the overall size of the model. To calculate an approximation of target strength or TS, an acoustic solid cubed model and the finite element method must be used. When the model is scaled up, the size of the personified region and as a result, the TS both increases in proportion to the model's size. It is reasonable to expect that hulls with greater thickness will have a higher target strength. It was noted that the frequency affected targeted range since diverse auditory modes would be activated. Because of the way targeted range operates, this would be the case. And here you can see that this represents the scattering object of the proposed submarine, the angle of incidence of the incidence field, and the related absorption coefficient for the visible surface are presented here. The visibility normal absorption. The visibility computation is critical to the asymptotic scattering approach because it estimates how much of the surfaces of the scattering subjects are actually exposed to the incident background field. And here you can see it displays the possibilities for observation in the current configuration of surface normal absorption. Acoustic pressure is measured using a logarithmic scale with the decibel serving as the standard unit of measurements. For a human to hear a sound for the first time, 20 micropascals of acoustic pressure are required. Because this is such a little amount, we must first convert pascals to decibels before using them in our daily work. When used as a measurement, 20 micropascals is normal taken as the standard for acoustic pressure. The total acoustic pressure, including both incident and dispersed wave, is measured at the seafloor and in the plane defined by Z is equal to 0, as shown here. And the zoom out view is represented such as here. The pattern is only partially resolved as a result of the low resolution of the evaluation grid, as a result of the fact that acoustic pressure has a connection that is inversely proportional to the distance from the source. It is vital to measure the object's distance from the source when observing an experiment that involves acoustic pressure. The relationship between acoustic pressure and the distance from the source follows the inverse square law, which states that the intensity of sound decreases, the square of distance from the source increases. Mathematically, this relationship can be expressed as the P is equal to P0 multiplied by R divided by 4 P are power to 2 and 5, where P is acoustic pressure at the given distance from the source. P0 is the reference pressure, usually taken at the threshold of human hearing, which is approximately 20 micropascals. As the amplitude of the sound wave, R is the distance from the source, and P is the mathematical constant, approximately equal to uh, 3.4159. According to the equation, as the distance r from the sound source increases, the denominator for phi r power by 2 becomes larger, resulting in a decrease in the acoustic pressure or P. This decrease happens because the sound energy is spread out over a large area as it propagates outward from the source. Thus, the inverse square law describes the gradual weakening of a sound intensity with increasing distance. Comparison tools. Comparison to the maximum level of sound that a human can hear is 1 decibel. Comparisons of sound levels use the value of 1 decibel as their starting point almost without exception. While calculating the acoustic pressure level, it is not necessary to take into consideration the distance that exists between the microphone and the source of the sound, and 1 meter is considered to be the minimum safe distances from any given sources. Exterior field pressure and the radiation pattern at 100 meter depicts the entire three-dimensional scattered sound pressure or level or SPL radiation pattern at a distance of the 100 meters. It is noted that the main lobe corresponds to the specular reflection of the aquatic body at its most superficial level. And here you can see that it depicts the comparable radiation pattern in the XY plane for any regulation performed 1000 meters from the source. The static target strength of the submarine is measured from the biostatic vantage point by a receiver placed at the same distance as the source. It depicts the scattered SPL sound pressure. On the other hand, it depicts the ballistic target strength for the specified source and scatter setup. It displays a three-dimensional representation of the scattered sound pressure level or SPL radiation pattern at the distance of 100 meters from the sound surface. This graph offers a valuable insights into how sound energy is scattered and distributed in space as a function of angle and frequency. Understanding the scattering behavior is crucial in characterizing the directivity of the sound source, which is essential in applications such as loudspeaker design, sonar system, or acoustic communication. By visualizing the three-dimensional radiation pattern, researchers can identify peaks and nulls in sound intensity, helping to optimize sound projection and reception in specific directions. It likely represents the radiation pattern of the sound source in the XY plane, providing a two-dimensional view of sound directionality. This graph helps us understand how the sound energy is distributed in the horizontal plane around the source. By analyzing the radiation pattern in this plane, researchers can gain insights into the source's directivity and coverage area. This is particularly useful in scenarios where sound needs to be focused or directed towards specific targets or areas, such as in public addresses systems or directional loudspeakers. And what about the ballistics target stage of submarines? It is important to note that a peak appears directly beneath the submarine and at the angle of the reflection from the source. Depending on the situation, sonar equipment can operate either aggressively or passively. The distinction between active and passive sonar is that the active sonar uses an active source to generate an acoustic signal which is then reflected on the submerged object. An active source is not used in passive sonar. Passive sonar, on the other hand, entails the sensor simply reflecting the sound made by the submarine while it is in its operation. Active sonar can be implemented in either a monostatic source and listening point in the same location, or a uh, biostatic source and listening point in different locations. Configuration in the capsule acoustic simulation models. It likely presents data on the exterior field pressure distribution around a sound source. This information is in it presents data on the scatter source pressure level of a submarine. This information is crucial for understanding how submarines interact acoustically with their underwater environment. The picture here likely depicts the variation in scatter sound levels as a function of frequency and angle, showing how much sound energy is reflected or scattered by the submarine hull and the other components. This knowledge is essential for accessing the submarine stealth capabilities, as a high scatter SPL can make the submarine more detectable for sonar system, impacting its effectiveness in military operations. It displays the ballistic target range of a submarine. BTS represents the submarine acoustic reflectivity or echo strength, indicating how much sound energy is reflected back to a sonar system when it encounters the submarine. A high BTS value indicates a strong echo return and making the submarine more detectable. This information is crucial for evaluating the submarine acoustic signature and vulnerability to detection by enemy sonar system. Reducing the BTS is a key consideration in submarine design to improve stealth and reduce the risk of the detection in naval operations. And what about the comparative analysis? Comparative analysis of simulation results aspect comparison criteria result in conclusion acoustic pressure frequency dependencies. The comparative investigation of the high-frequency asymptotic scattering model for the acoustic target strange of the underwater submarine vehicle yields interesting results as depicted in the parameter table. First, in terms of acoustic pressure, the model shows a good arrangement with experimental data at high frequency, demonstrating its accuracy in forecasting the acoustic pressure response. Second, when compared to the reference model, the model successfully captures identical directivity patterns for the scattered sound pressure level or SPL radiation pattern at 1,100 meters, suggesting its capacity to properly reflect the scatter SPL pattern. Furthermore, the model produces a consistent finding in the horizontal directivity of the X and Y plane, demonstrating good agreement with experimental data. Furthermore, the model is resilient with small functional fluctuations in the scatter SPL. of the submarine seen under various parameter settings, providing its usefulness in mimicking the submarine acoustic behavior. Finally, in terms of the submarine ballistic target range, the model yields reasonably accurate predictions that are consistent with the reference model, uh, bolstering its dependability for estimating the submarine acoustic detectability. Overall, the high-frequency asymptotic scattering model shows promise in accurately modeling the acoustic target range of underwater submarine vehicles, making it a viable tool for real-world acoustic analysis. And what about the research questions and answer? The first one is, how can the acoustic target range of an underwater submarine vehicles be effectively modeled using high-frequency asymptotic scattering? The answer is the modeling and underwater submarine vehicles acoustic target stage for high-frequency asymptotic scattering involves various considerations and methodologies. The target stage, or TS, of an object refers to the amount of sound energy that is scattered back towards the source when it's illuminated with sound waves. The next question is, how can the high-frequency asymptotic scatter model be applied to underwater submarines? The answer is, the high-frequency asymptotic scattering model can be applied to underwater submarine by considering their complex shape and structure and using appropriate asymptotic techniques to approximate the scattering response. This involves deriving and solving the scattering equations that account for the submarine's geometry and material properties. And the next question, third question, is how accurate and reliable is the high frequency asymptotic scattering model compared to the other model and other methods? The answer is, the accuracy and reliability of the high-frequency asymptotic scattering model depends on various factors such as the complexity of the submarine geometry, the frequency of the incident sound, and the level of approximation used. In certain scenarios, high-frequency asymptotic scattering can provide accurate results while being computationally more efficient than full-wave numerical simulations. And what about the conclusion? As a part of this study, we compared the target stage across the variety incident, acoustic wave frequencies, and sweeping angles, as well as across three distinct vehicle shape magnifications and the whole thickness. This was done in the order to better understand how the target responds to change in these factors. In addition, the frequency of the sound waves and the direction from the which they are approaching is analyzed to visualize the finding of the far field computation that was based on the Helmholtz-Kirchhoff integral theorem. We made use of the finite element method analysis tool or capsule multiphysics, and this program allowed us to visualize the result in a way that was easier to understand. According to the findings of the research, one of the most important aspects of the steel design calibrating the characteristics acoustic impedance. By adding the coating, it is possible to significantly lessen the intensity of the target. The larger the submarine, the greater the amount of pressure that will apply to the target. In addition, the higher the frequency at which a sonar system works, the greater the likelihood that it will be attract attention. As a frequency of this, a submarine vehicle will have high frequency protection against anti-radiation integrated into its architecture. In future, we extend to improve the computational modeling techniques and enhance the understanding of high-frequency asymptotic scattering in underwater environments. And here we can see this is a submarine and the medium of water. And the physics that I have used is pressure acoustic and asymptotic scattering. And the material which I have used is water as a liquid. And you can see the three-dimensional scatter SPLs. And here you can see we can change the transparency here, which you can see through this here. This is the submarine and which radiation pattern. Its shape such as a sphere. The next one is exterior field pressure at 100 meter. The next one is a plot, a scattered SPL in x-ray plane. The next one is such as the radar. It has a 300 uh, near to zero, 360 degrees. And the next one is acoustic pressure. It's based on the Pascal. The next one is visibility. And you can see that how much the visibility there is. You can see that at the top surface, the visibility is very zero. Here you can see that it's zero, but the other section of the body is not covered completely. An angle of incidence. You can see that the tail has the most angle of incidence. The next one is surface normal absorption. And the last one is ballistic target strength and scatter SPL. Thank you so much for watching my video until the end, and also you can download this tutorial video from github.com/mahsascript.